Uh, yeah. Are we filming? I guess so. It's 1:14 p.m. here, and I think I'm about to go half crazy. I got so much freaking shit to do, you guys. But I wanted to hop on here and see what everyone is up to, and I want to see if you know. I don't know. I just need to keep myself occupied lately, because shit. Whenever I'm not working out or on the go, on the move, intrusive thoughts sometimes, I struggle with all these fucking intrusive thoughts sometimes. Pain in the ass. Uh, Fuck. I hope I didn't pull out mine. No, here's mine.
Alright, so welcome to this.
Fucking. I did buys and tries and forearms and yeah, all those types of exercises yesterday for y'all guys who saw my stream yesterday. Uh, so so yesterday I did arms. Of course, I did arms, buys, tries, forearms yesterday for those of y'all guys who saw my live stream yesterday. And fuck, you know, I feel like most times I either have to be exercising or on the move so I can keep myself occupied. It's we got yeah, Fox Dorito. Hi, Fox Dorito. Senvi. Yo, what's up? How you doing? Yo. Now we're starting to see more people on here. That's what the hell I like to see. That's what I'm talking about. The Mad Lad says, "Can I have $1?" I'm a dirt poor son of a bitch. Hello. Uh, I ain't got no money for y'all. English. Y'all guys are funny as hell. What to do? John Dexter says, "What's up? What's up? How you doing, man?" Not much. Just doing a little bit of Not much, just doing a little bit of school shit. Yeah, I figured my video froze a little bit. Is it working good now? Flipborn says I'm new here. Well, welcome. All right, cool. That's good to hear that. We got. Yeah, that's a funny username there. Avocado, I'd say. I've got to have avocado. Dang, I need to brush this beard out. English. To answer your question. Uh. I don't know. I gotta brush it out. Which is reminding me. Michael Bandel. Oh yes, I've heard of that one before. That's fucking funny. My brother told me that one time. I have plenty of worse jokes I have plenty of worse jokes I could tell you. But maybe that's for another time. Okay. Let's see if this freaking beard is looking better now. Jose Malone. Ah. Thanks. Oh yeah. Yeah. Where are all y'all guys from on here? Ah, shit. I love both, honestly. I haven't been four-wheeling in a long while because my fucking gas line broke for the third time about 3-ish years ago. But next time I come down here ways, I ain't saying where I am, but I'm definitely gonna get a quad trailer and bring my I got a big old Yamaha Grizzly I'm gonna get that fixed up. Do some riding around here. Yeah. But yeah, I've been doing a lot more driving lately. It's like I picked up not a shit box. I picked up an older car off of Facebook Marketplace a while back, and it's been getting me, where I need to go and all that. And have I seen a grizzly bear? I've seen black bears. There's black bears, plenty of black bears around where I live, though. Never a grizzly though. Around here, there's actually a couple kind of, I guess you could say, predatory cats, wild cats. Well, I've seen around here they actually have lynx, like and bobcats. I saw it was either a lynx or a bobcat that I saw the other day when I was just walking. Grizzly cats, nah. Um, I, I don't really play a lot of video games that much no more. But I'm considering. Uh, at some point, I'm probably gonna buy a PlayStation or something. I don't know. Bears are just cuddle poodles. You say that until they'll tear you. If you fuck with them, they'll tear you limb from limb. You know. But black bears, however, they they're not like predatory, so to speak, because they'd be more scared of you than you would be of them. You know. Oh, oh, the ones at the bar. Oh yeah, I knew. I figured. I was wondering about that for a minute. I figured you all guys were talking about something a little, you know. Oh. Okay. Fuck. Nah, I can't do none of that. I don't like giving out. I don't like giving out what my location. I don't like doing that. In this, in this module, you will explore hypothesis tests. These are very useful tools for analyzing data sets and deciding if there's enough evidence to reject the null hypothesis or not. Throughout this module, I encourage you to blah blah blah. I'm not gonna read that whole fucking thing. Uh, Module overview. This is fuck. Available on July 4th, due August 4th. Fuck that. Sometimes I wonder why I'm even still in college, because it's like, fuck this. It's like just keeping me on the fucking computer all the fucking time. Okay, you take care. Roblox Addicted says hi. XSU2E. Yeah, shout out to you, wherever you are. Thanks for tuning in. If you could do me a favor when you're done here, can you share my channel around? I'd like to get a couple more subscribers. I'd like to increase my subscribers. By no means do y'all get Skank Hunt. Welcome back. Welcome back. All right, thank you for that. I appreciate that. Yeah, I want to see if I can get up to 5. They're saying 500 subscribers now. For goodbye. Bye for now. What was it? In this module, you will. Not every day. I do. It varies. It depends. Hypothesis testing. This is going to be a very intense week, and if you have any hypothesis, I know what a hypothesis is. A hypothesis is a statement that can be supported or rejected based on observations or actions. The H naught is a hypothesis, the initial statement, and H1 or HA, the alternative. Thank you. Is an alternative hypothesis that challenges the first one. Simple example, someone is arrested and waiting for a trial by jury. The suspect is presumed innocent until proven guilty. With errors type 1 and 2, the difference is if the initial hypothesis is true but rejected by the outcome, then that is a type 1 error. If the initial hypothesis is false but not rejected, then that is a type 2 error. The person arrested is either innocent or not innocent, and the jury has the option of guilty or not guilty. Looking at the outcomes, the suspect is innocent and is found not guilty. Yeah, no shit. Thank you. You have a great day too. The suspect is innocent and found not guilty. Do not reject the null hypothesis. H naught is true. The suspect is not guilty. The suspect is not guilty. The suspect is not innocent and is found guilty. Reject the null hypothesis. The suspect is innocent and is found guilty. The initial hypothesis was valid, but was rejected. Type 1 error. The suspect is not innocent and is found guilty. And is found not guilty. Failed to reject the alternative. Give me the 500 subs. Wow.
Alright, so welcome to this demonstration on the very basics of hypothesis testing. And as I've written there, there's going to be no maths in this demonstration, so but you can take a breather. This is just designed to give you the overall concepts and develop your intuition about how hypothesis testing actually works. And to some degree, this is going to be more important than actually learning all those formula later on. And I'll bet you by the end of all this, you'll have a really good foundation for all of your subsequent work with hypothesis testing. So let's get straight into it. I'm going to present you with a hypothesis. This is my hypothesis, Justin's hypothesis. The average height of students at university is 175 centimeters. Now let's ignore the potential differences in height between men and women. Let's just keep it simple. And yes, while we call this a hypothesis just in normal English, the term hypothesis actually has a specific meaning in statistics as something which we can put to the test. So let's try and do that by taking a sample. Here we've got a sample of 20 students, and the average height of these students is 174.6 centimeters. Now I'm going to ask you, how much doubt do you think this casts on my hypothesis? Now I've said I think the average height is 175 centimeters. We've got a small sample and it appears to be slightly less than that. But does that really cast a lot of doubt on my hypothesis? Probably not, right? I mean, you understand the concept of random variation. And here, we've got a random selection of 20 students, and it's possible that they just were slightly less than the true average, which might still be 175 centimeters. So it's not outside of the realms of possibility that my hypothesis is still correct. Now, let me ask you this. Imagine we've taken another sample, or let's just say that turned out differently, and the average height was 168.4 centimeters. So that's now a little bit further away from 175. So how much doubt does this cast on my hypothesis, do you think? This is probably going to cast more doubt than the last example, because even though we have the same number of people in our sample, their average height is quite a bit lower than 175. So you've got to start thinking, well, how likely is it that the true mean is 175? How likely is it that this sample is just randomly less than the true mean? Believe it or not, you've just done your first hypothesis test. I know we haven't dealt with any formula or numbers yet, but
this is just foreign language
just
to me.
what
I don't
hypothesis
fucking
testing
know what
is.
this means.
So to be more specific, we call that original hypothesis the null hypothesis.
I'm gonna have to watch this
And we
fucking
give
thing
that
over again?
the
I don't give
symbol
a fuck.
H subscript 0 or H naught. And that null hypothesis was that the true mean was 175. And we've got this other thing called the alternate hypothesis, H1 or HA as it's sometimes written. And under the alternate hypothesis, the true mean is actually not 175. So the question is our sample mean far enough away from 175 centimeters for us to be able to reject that original hypothesis? And you've just done that yourself. in that second example there, you thought, maybe it is far enough away from 175. Maybe there is now quite a bit of doubt cast over that null hypothesis. Let's consider this number line the possible values of x bar. You can see I've written x bar on the right there. Now that is the symbol we use for the sample mean. Now if the true population mean was 175 centimeters, if you took a sample, you're still probably expecting that sample mean to be 175 centimeters. But of course we know that due to random variation, it won't necessarily match up with that exactly. It could be, say, 174, it could be 176. But what a hypothesis test will do will be to set these critical values beyond which we're going to start saying, you know what, let's reject that null hypothesis. So when our sample gets too extreme, we start casting a lot of doubt on that null hypothesis. So with our example, at 168.4 centimeters, that was our sample mean, that could well be in that rejection region on the left there. So maybe that is too far away from 175. Now let's try another example. Let's say that Louisa has a hypothesis that she says that the average age of postgraduate students at university is 31. Again, how are we going to test this? Well, we're going to have to take a sample. And let's say we've taken a sample of only 5 students this time, and we've found that their average age is 34. Here's my question again. How much doubt does this cast on Louisa's hypothesis? So I hope you're getting the gist now. If it's 34, you might think, even though it's slightly higher than 31, which was Louisa's hypothesis, we've only got a sample of 5 students. And maybe we just selected 5 that were a little bit older than the average, and if we selected another 5, maybe that average age would be a lot lower than that. So you probably think, it doesn't cast that much doubt at this stage. But let me ask you this. Imagine something but took a sample of 200 students and found that the average age was 34. If I asked you again how much doubt this casts on Louisa's hypothesis, you're going to start thinking that, yeah, that is casting a lot of doubt. The average age hasn't changed of our sample, but what has changed is the number of observations in the sample. So we now have 200 students in the sample. So what that means is that we're more confident about the precision of that sample mean. And I think intuitively you can kind of see this work, right? Imagine you had a huge sample and found the average age was 34. You're going to start thinking, well, we've pretty much got almost the entire campus here. The true average age is probably not going to be 31 anymore. So if we just line this up again, our null hypothesis here is that the true population mean was 31, and our alternate hypothesis is that it's not 31. So in our sample of 5 students, those critical values that we would draw here to determine whether we would reject that null hypothesis might be far away from 31. But when we had 200 people in our sample, those critical values beyond which we're going to reject that null hypothesis are actually quite close to 31 itself. So if we get a sample mean up at, say, 32 or maybe 33, maybe that's enough evidence here to reject that null hypothesis. Now, I haven't done any actual calculations here yet, but there will be ways for us to calculate those exact regions to determine whether we're going to reject that null hypothesis or not. And that fun is waiting for you in subsequent videos. But the question that we're really asking is this. If the null hypothesis were true, how extreme is our sample? This really is the core question that a hypothesis test tries to answer numerically. And while I've promised you we're not going to get too mathematical, just as a heads up, you'll get a formula that might look a little bit like this. And this Z is a measure of that extremeness. So when Z is close to 0, that means that our sample lines up pretty much with what we would expect if the null hypothesis was true. And if you have a look at the numerator of that function, you can see that if the sample mean equals the hypothesized mean mu, then we're going to get 0. And the larger that gap between x and mu, the larger the Z value, meaning our sample is more extreme. And this means we're more likely to reject the null hypothesis. And we saw this happen with Justin's hypothesis at the beginning of this video. And also you might notice on the denominator there's an n down there, And we now understand how that works too, because as n increases, that value of z will also increase. Meaning again that we're more likely to reject the null, as we saw in Louisa's example. Now the sigma in that formula represents the underlying standard deviation, but that's at least the formula explained. So just in this very theoretical example we've done, we know that we're more likely to reject H0 when the sample difference is greater, like in Justin's example, and when the number of observations is greater, like Louisa's example. Now this brings us to our final concept, which is type 1 and type 2 errors. Now let's go back to the original example where the null hypothesis was that the population mean was 175 centimeters, and we're trying to see if there's enough evidence to reject that. One key principle you have to keep in mind is that we can never disprove that null hypothesis. You're never going to use the word proof in any of this stuff, because even when the true population mean is 175 centimeters, it's still a sample. So you're never going to disprove it, and thus there's a possibility of you incorrectly rejecting it. And that's what a type 1 error is about. So remember this, remember how we had our regions where we were going to reject the null hypothesis? A type 1 error occurs when you reject a null hypothesis that is in fact true. So if our sample mean lay in those rejection regions and we therefore rejected that null, it's still possible that that null hypothesis was true, don't forget. We can never remove that probability of a type 1 error. And in fact, we give that a name. The probability of a type 1 error is called the level of significance, or alpha. And you can actually choose your level of significance. You can choose how strict you're being with your decision to reject that null hypothesis. And often we're going to use a level of 5%. That's just the convention. But just appreciate that these regions that we've drawn up here, where we're going to reject that null hypothesis, are completely arbitrary. We've just decided on them based on this level of strictness that we can call the significance level. Now you might be able to guess what a type 2 error is. Here's that rejection region again from that first example. A type 2 error occurs when you do not reject a null hypothesis that is in fact false. So say our sample mean lay very close to 175, and we therefore chose not to reject that null hypothesis. It is of course still possible that the true population mean is different from 175. I mean, it could be anything, and in that case we'd be committing a type 2 error. And again, this probability of committing a type 2 error is something we can't fully mitigate. There's always going to be a probability of committing a type 2 error when we conduct a hypothesis test. In this case, the probability of doing so for a type 2 error is called beta. And for your own knowledge, 1 minus beta is called the power of the hypothesis test. So if beta is the probability of a type 2 error, which is not rejecting a null hypothesis that is in fact false.
We got Jonathan Santos.
Rejecting a null hypothesis.
Hey, Jonathan Santos, how are you doing?
False, which is what we'd want to do if the null hypothesis was false, right? We'd hope that we would reject it. And the chance of us doing that is the model's power. So that's it. That's my brief introduction to hypothesis testing. And you can continue on to the next video if you'd like, where we start getting down and dirty with the mathematics.
As you should be. Videos. So any of y'all guys on here at the moment, you'll see the other live I did yesterday. That was my arm workout. It was exclusively arms, like all things arms. And I had to sort of adapt to what I had available to me. Like for the month that I've been, let's just say, out of town. Away. from civilization. Anyways, the entire month I've been doing mostly the adaptive stuff, like with the Bowflex machines, and with some of the exercises, like the curls, for example, when you stand up. I mean, yes, it enables you to have like a proper range of motion, but I feel like the little balls at the ends of like the cables, they hit the machine like right as you go all the way down. I don't know if that takes away from uh, making them like proper, if you know what I'm trying to get at. But yeah, I've been trying to keep myself physically in shape, keeping myself in decent physical shape, because that helps me mentally too. That's a big thing. That's like my folks like to give me. Nah, I take that back. I exaggerate a little bit on what I'm about to say. My mother, every once in a while likes to give me grief for how much I work out and all that. But you know, what she doesn't understand is if if I were to explain to her on a deeper level what working out and lifting weights has done for me overall, she will she will encourage me to do that as much as I possibly want to. But you know, it is how it is. Where the heck are these videos that I'm supposed to watch? Hypothesis testing when the standard deviation is known. I'm probably gonna bore y'all guys all to shit.
In this video, we're looking at the hypothesis test for the mean mu when the population standard deviation.
Oh no, 16 minutes. I gotta sit through a 16-minute video for fuck's sake. That's just great. Ramcat says, "Hey, you're live again." Yeah. I figured why not. Yeah. I figured I'd hop on for a little bit. Yeah, I remember you. Heck yeah, I remember you. I think it's cool. I think it's cool to see regular. I think it's cool to see that I have a bunch of regular. Ah, dang it! The video cut out on me, probably. But yeah, I think it's cool to see the regular bunch of regular, returning viewers and subscribers come back and join me again in this little crazy YouTube video making journey that I got going on. Place I can plug this in. I don't know if I'm going to sit through this whole all these videos.
It follows on from a couple of videos on the basics of hypothesis testing, which I am going to recommend you watch if you're a newbie to all this, as it'll help develop your
Oh, this guy can read my mind. I am a fucking newbie. I think he's insinuating that. I think he's trying to insinuate that he's better than me. This YouTube fella on here. I think he's just insinuating that he's somehow better than me, which I don't care, but.
intuition around some of these complex concepts. There'll be a link in the description for that. But here, though, we're going to jump straight into an example to learn by doing. Now, don't be put off by the length of this question. It's a classic hypothesis testing scenario. So let's give it a read. The manager of a department...
I'm not going to read this whole damn thing.
Now, these are often given the symbols H0 and H1. And this is potentially the most difficult part of the whole operation. Often it's difficult to determine exactly what is being tested. So let's have a look at these couple of lines. It says, she determines the new system will be cost effective.
Well, I'm sorry, but I gotta go, and I just want to say hi. Thank you for just stopping in and saying hello. Good to see you again.
Only if the mean monthly account is greater than $70. And the question is, can we conclude that it will be cost effective? So my hot tip for creating null and alternate hypotheses is to put whatever you are seeking evidence for in the alternate hypothesis. So here we're trying to seek evidence that the true population monthly account value is greater than $70. And that goes in our alternate hypothesis, meaning that our null hypothesis is simply that it's equal to $70. Now, some people might like putting mu is less than or equal to $70 in the null hypothesis, but really that just depends on the particular convention. The important thing to note, though, and I'll repeat this, the thing we are seeking evidence for goes in the alternate hypothesis. Now, why is that? Well, if we're seeking evidence for something, but start with that as our null hypothesis, the mere fact that we can't reject that null hypothesis is not a very strong statement, is it? So rather, what we do, if we're trying to seek evidence that the mean is greater than 70, is start with the assumption that it's not greater than 70. Let's start with the assumption, or the hypothesis, that it is in fact exactly equal to 70, and let's see if we've got the information to reject that. And in doing so, we'd make a very strong statement in favour of it being greater than $70. So hopefully you can see then that whatever we seek evidence for needs to be in the alternate hypothesis. So really what's happening here is that under the assumption the null hypothesis is true, there's going to be some distribution about the possible sample mean values. So there's a distribution with a mean of 70, and we actually have a sample mean of 74. So really the question we're going to be answering is, how extreme is that 74 value? Is that value so extreme that it will cast doubt on our null hypothesis? Well, that's what a hypothesis test effectively does. And in our next step, when we calculate the test statistic, we'll be quantifying how extreme our sample is. But first, let's just write down the information that we have. There's X bar, which is our sample mean at 74. The population standard deviation is 30, and we have 200 observations in our sample. Now, because sigma is known, we can use Z as our test statistic. And putting in all our information into the Z formula there, we can find that Z equals 1.8856. Now, as I've said in previous videos, this is some indication of how extreme our test statistic is, that's 74, if the null hypothesis was true. And the higher the Z value, the more extreme our sample is. So the more doubt then it casts on our null hypothesis. But at what point do we say, you know what, that's too much doubt on our null hypothesis? Well, that's where the decision rule comes in. So if the null hypothesis was true, our test statistic should be distributed normally with a mean of 0 and a standard deviation of 1. So we'd be expecting a Z value of 0, but of course, due to random variation in our sample, we'd allow a little bit of tolerance either way. But this is where the level of significance comes into play. For a 5% level of significance, we can construct for ourselves this rejection region, above which lies 5% distribution. So that means that if our test statistic is so extreme that it's in the upper 5% of possible values, we're going to reject null hypothesis and say, you know what, our sample's now too extreme. Now, how do we get this value? You can use tables to find this, and feel free to look in the description for my video on using distribution tables. But no doubt we can use Excel as well. So here's the formula that Excel will require for you to calculate a Z critical value. It's norm.s.inv, and inside that bracket, you put the cumulative distribution at that point, or the CDF. So I've put 0.95 in this Excel function here, because I know that at this point of interest, there's 95% of the distribution before it, as in to the left of it, leaving 0.5 above it. So when I put all this in, I get a Z critical value of 1.645 coming back at me. Great. So that means we're going to reject this null hypothesis if our Z value is greater than 1.645. Now you're very welcome to then go on to steps 4 and 5, but I thought I might put a little step 3a in here, just to discuss the concept of p-values, because there's two kind of ways of coming at this. Now, a p-value is the probability of getting a sample as extreme as ours, given the null hypothesis is true. So in our case, you can see we've got a Z value of 1.886. So really the question is, what's the probability of getting a test statistic equal to or greater than that? And using Excel, you can use the norm_s_dist function that provides for you the area to the left of a certain Z value. So in this case, if I do norm_s_dist and I put 1.886, it'll provide for me the area to the left of 1.886. Of course, we need the area to the right, so we've got to go 1 minus that figure to get 0.03. Now this true value here that I've put into the norm_s_dist function just tells Excel that yes, indeed, I want the cumulative distribution function, the CDF. If you were to put false in there, you'll be getting what's called the p-value of this, so it gives us the area to the left of a certain Z value. So we know that the p-value then is 0.03. Step 4 then is to state our rejection decision. So using the rejection region we calculated first, we can say that we reject the null hypothesis of 5% of the significance, as Z is greater than 1.645. Or alternatively, given we've just calculated the p-value, again we can say that we reject the null hypothesis at that level of significance, as p is less than 0.05. And with p-values, we know that we reject the null hypothesis if p is less than the level of significance, which in this case is 5%. Now, appreciate that these two methods of stating your rejection decision will always be in agreement with one another. They're exactly the same test, just looked at from a different perspective. This one looks at it from the perspective of the population mean, or what we're testing it against. And this one comes at it from the point of view of the test statistic itself. And in either way, we're going to reject this null hypothesis, leaving us with the conclusion that there is enough evidence at the 5% level of significance to suggest that the mean monthly account is greater than 7. So that means our sample mean was indeed far enough away from what we were testing against of $70 for us to reject this null hypothesis. Now appreciate that this was a one-tailed test. We were only ready to reject the null hypothesis if the sample mean was in one direction of that hypothesized mean, in the positive direction. Here's an example that's a little bit different, so I'll give you some time to have a read of that. And again, if you'd like to pause the video and come up with your own answer, you can see if we get the same answer. But we'll do a quick reading here. A new toll road is being built and financed with the expectation that 8,500 cars will use it per day. Now you've got to keep in mind that with these kind of expectations, it's actually bad if you overestimate or underestimate the number of cars that will use it. I mean, if you overestimate, then you're obviously not going to get as much money back from the tolls. But if you underestimate it, maybe you could have spent more money on the road itself or made more lanes or something like that. So it's quite important to get a reasonably accurate picture of how many cars use this toll road. So it says that in the first 30 days of the operation, a daily average of 8,120 cars were used. One to test whether the expectation was incorrect. Again, we've got that sentence. Assume the distribution of road users is normally distributed with a standard deviation of 950. So I'm going to do this one a little bit quicker, but here's the null and alternate hypotheses. Appreciating that the alternate hypothesis is simply that it's not equal to 8,500. That's what we're seeking evidence for in this case. So it goes in our alternate hypothesis. So we would be rejecting that null hypothesis either way, whether our sample mean is significantly more or significantly less than 8,500. And our sample mean we got was 8,120. So is that far enough away from 8,500 for us to reject that null hypothesis? Well, let's find out. The first thing we can do is calculate the test statistic. As we did last time, there's x bar, sigma, and n, and we find a z value of minus 2.191. Now, is that going to be in our rejection region? Well, here's our decision rule. Again, it's going to be a z distribution, or a normal distribution with a mean of 0 and a standard deviation of 1. But there are two differences in this example. Firstly, we know it's a 1% level of significance. But secondly, we know it's a two-tailed test. So that 1% rejection region needs to be split into the two sides, leaving 0.005 or 0.5% in each 576. I need to tell Excel, well, find me the z value below which lies 0.995. So even though this is a 1% level of significance, this value here has to be 0.995 to get the appropriate point above which lies 0.005. That's 2.567. So we're going to reject this time if z is greater than 2.567 or less than negative 2.567. So we can calculate the p-value again, noting that it's the probability of getting a sample as extreme or more extreme than ours, given the null hypothesis. Is true. So here's our z statistic minus 2.191. So if we wanted to find that shaded region below it, then we can use this norm.s.dist function to find that at 0.0142. But given this is a two-tailed test, we have to appreciate that we can be more extreme than this test statistic in either direction. So values up here on the positive side are technically more extreme than ours as well. So for a two-tailed test, you have to make sure you multiply this area by 2. And there we get a p-value of 0.0285. So again, our rejection decision, we either do not reject the null hypothesis, looking at our z statistic because it's between minus 2.567 and 2.567, or we can say we do not reject because the p-value is greater than 0.01, realizing that it's a 1% level of significance we're using here. So our conclusion here is that there's not enough evidence to find we tick.
So it's due on the 11th. Damn. Fuck that.
In this video, we're going to do a hypothesis test for mu, that's the population mean, when the population standard deviation is unknown. Now this is a bit more realistic than previous examples because in reality, you're not going to know the population standard deviation. Any kind of sample or survey or anything like that will be relying upon the sample data only. So let's get stuck straight into it. Here's a question in which we've provided a data set for you to calculate stuff from scratch. And I'd suggest if you're comfortable pausing the video now, giving the question a go, and then seeing if we get the same answers. It goes like this.
I can't answer this shit to save my life.
ShowDonkey advertises that its average delivery time is less than 6 hours to deliver. The first ever shows in our reject. Now I've made a video to explain this equals variable input 8 for for us. Step 3.
I honestly don't know what the hell any of this
1.4
shit means. So
1.05. And just
What the
remember that
fuck?
either one you use, they'll always be in agreement with each other. So if you find that one of them tells you to reject and the other one says do not reject, then you've done something wrong. So it's a good check to see if you've got the answer right. So a conclusion then is that while the sample mean was 5.6 hours, there is not enough evidence watching.
yeah, that's 9 minutes of my life I'll never get back.
In this video, we're going to do a hype.
Hey, Grandma. You going to Russellton? Okay.
Do you need anything, want one?
I'm okay.
Huh?
I'm all right.
Stop and see. Tony can open my glove compartment. Huh, see that picture? That was when I had, was my prom.
Oh.
Many years ago. Okay.
Grandma, I love you.
I love you too, baby.
I wish I didn't have to spend so much time on the computer. That's.
Well, you get stuff done in the morning pretty much.
I
You
try.
have all the afternoon and evening, so
Yeah.
it's okay. Hey, it could be worse.
Right.
At least you can do it here and not at home.
Oh yeah, I agree. Damn it, man. Should I try the first homework? That'll take me 2 fucking hours. Yeah, that'll be fucking great. Okay, we've been rolling for an hour and two. Just damn it. Thank you for those who tuned in and for those who are returning, and thank you for being a subscriber. Thank you for joining me here. I hope to see y'all guys soon again. See you.